And so now I'm very happy to introduce today's speaker. So we have John Nichol from the University of Rochester. He started out at St. Olaf and he was in the band instead of the choir. He was not the most famous musical ensemble of his undergrad. Sorry, inside joke. And then from there, he went to UIUC for graduate school and a postdoc at Harvard. And he's been faculty at the University of Rochester since 2016. He works in the field of semiconductor qubits. And so he will be telling us about latest developments there.
Okay, well, thanks very much for the introduction and for the invitation to be here with you today. Had a great day so far. I'm looking forward to some more interesting conversations. So I'm going to tell you about the nuclear spin dark state in silicon. Before I get into the details, I want to acknowledge that the work that I'll tell you about today was done mostly by my postdoc, Shinshin Kai, and graduate student Habitama Walaline. And this was funded by the Army Research Office. And the dark states that they can form. I'll tell you about some of the data that we've taken and how we understand this data. And then I'll tell you about where we want to go from there. And please don't hesitate to ask questions if any come up. Okay, so you know this, I know this, but let's just agree to be happy that nuclear spins are everywhere. Okay, our bodies are full of 10 to the 23 nuclear spins in the form of protons. And the ability for scientists to manipulate these nuclear spins has profoundly shaped both science and medicine. Okay, in the case of medicine, magnetic resonance imaging allows us to look inside human bodies by interrogating the nuclear spins that are present in them. And then in a related technology, but let's say within the realm of science, nuclear magnetic resonance spectroscopy allows us to look inside materials. It allows us, for example, to look inside semiconductors and find out what's happening with the electronic spin states involved by looking at the nuclear spins. Okay, so this also plays out not just in kind of the macroscopic world, but also in the quantum world on the nanoscale. So here again, nuclear spins are important. They play a major role. Here's an example of an electron spin qubit associated with the nitrogen vacancy center in diamond. Okay, it's surrounded by a large number of carbon-13 nuclei. The same can happen when we talk about electron spin qubits associated with phosphorus donors and the nearby nuclear spins in that system as well. So in this case, also the ability to manipulate the nuclear spins has had profound impacts on the development of quantum information processing devices. But one new twist here is that these nuclear spins often form an uncontrolled environment that can cause bad things like relaxation or decoherence or what have you. So wouldn't it be nice if we could just polarize all of nuclei and be done with a lot of these issues? Wouldn't it be nice if we could just have them all point up, freeze them like that, and then have that be the end of the story? Then the signals we would measure in magnetic resonance imaging would be orders of magnitude larger. There would be no more fluctuating environments for quantum systems as a result of nuclear spins. That would be nice, okay? But you know that this is really hard to do. Why is this really hard to do? Well, it has to do with the fact that the magnetic moment of a nuclear spin is roughly 500 times smaller than the magnetic moment of an electron spin. So if we take the typical Curie law for paramagnetic magnetization, so if we ask, given an external magnetic field B acting on a magnetic moment mu at temperature T, what is the magnetization of the resulting, what is the resulting magnetization of a spin ensemble? For, let's say, regular electrons at 4 Kelvin and a modest field of 5 Tesla, they're mostly polarized, 90% or so. But if we ask about, let's say, protons in the same conditions, they are not polarized at all to any significant degree. And you can see that this problem gets a lot worse at room temperature. And this is one of the main challenges, for example, in conventional magnetic resonance imaging. Okay, so wouldn't it be nice if we could polarize all the nuclei? Yes, it would, but that's quite challenging. One of the ways that this is possible is through a process called dynamic nuclear polarization. So this is going to be kind of the background for what I'll tell you about today. So dynamic nuclear polarization can happen as a result of the electron nuclear hyperfine interaction. So this is the interaction between the electron spin s and the nuclear spin I. For the talk today, the most relevant part of this is what's called the Fermi contact interaction. So this has a term that looks like I dot s, and then also it involves the modulus squared of the electronic wave function at the location of the nucleus. So this is an effective I dot s interaction that results from the electronic wave function actually overlapping the nucleus in question. Okay, so what does this do? Well, you can see that this interaction Hamiltonian I dot s has the same energy if, let's say, S and I are like this or like this. So this interaction Hamiltonian will allow flip-flops between the electron and nuclear spin. And so you see that if I have the ability to polarize the electron spin, for example, here S, I can transfer that angular momentum to the nuclear spin subsystem by essentially allowing this Hamiltonian to act on the system and cause these spin flip-flops. All right. So this is in a nutshell how dynamic nuclear polarization can work. If we polarize the electron spins, we can exploit this Fermi contact interaction to transfer angular momentum to the nuclear spins. All right. So you can buy a very fancy NMR DNP system. So here, this is a 525 gigahertz NMR DNP system. You need a large field to Zeeman split the nuclei. But if you have this large field, you also need a very large frequency to address the nuclear spins. And by essentially driving the electron spins just a little bit off resonance, where the difference is the nuclear spin Zeeman splitting, you can transfer polarization from the electron to the nuclear spins. All right, so this is something that happens all the time with NMR spectrometers. These same ideas also play out in semiconductor quantum dots. So here we imagine trapping an electron spin in a confinement potential, and it interacts with the nuclear spins in the semiconductor lattice in the system. So this is going to be what the system I'll tell you about today involves. So I'll say a little bit more as the talk unfolds about DNP and semiconductor quantum dots, but here's just a little bit to give you a taste. So DNP, dynamic nuclear polarization, has been known to occur in quantum dots for quite some time. By the way, as I mentioned before, a quantum dot is just a three-dimensional confinement potential for electrons. Typically, these are made out of semiconductors. So the relevant size of the electronic wave function, which would otherwise be an extended block electron, becomes set by the size of this confinement potential we impose. So in particular, it can be tens of nanometers or so in spatial extent, and it can overlap a large number of nuclear spins. In things called self-assembled quantum dots, which are optically addressable, one can measure the Zeeman energy of spin states by looking at the differences in optical transition energies. And what's been seen is that the Zeeman splitting of these spin states depends on the polarization of the light, as well as the power of the incident light. And what we understand this to be a result of is that the electronic spins polarize the nuclei, effectively creating a different Zeeman field that the electron spin experiences. And so here in this panel, on the y-axis is the Zeeman splitting of a particular excitonic transition. On the x-axis is the excitation power. And you can see if you use the sigma plus excitation, as you go up, the Zeeman splitting increases. And then as you decrease the power, it stays high like this. And the interpretation here is that the electron is polarizing the nuclei as a result of the absorption of this light. And this kind of a hysteretic or locking behavior has been observed many times in these systems. Okay, similar kinds of things have been observed in gate-defined quantum dots. This is the system I'll tell you about today. These are similar hysteretic. Yes.
So PL is a complicated business, right?
Yes.
There's all this inelastic scattering.
Yes.
Are there also like absorption measurements that should direct absorption measurements?
You know, I am not entirely sure. Most of the rest of this talk will be on a different platform, which is kind of my home base. It's a good question. The overall point is that something is going on which has long been understood to result from dynamic nuclear polarization. Here in gate-defined quantum dots, this is what I'll tell you about today. Again, these kinds of hysteretic effects have been observed. Here's an example of an experiment where they continuously irradiate the electron spin with microwaves. And at the same time, they're changing the external magnetic field. The expected resonance frequency of the electron should follow this line. But there's a tendency for this resonance frequency to be suppressed and sort of locked and dragged again by the nuclei in the system. Like I say, this is all just to say that unusual and interesting effects associated with DNP have long been observed in these systems. A major motivation for understanding and exploring DNP in these systems has been to achieve what I described as a main goal earlier. Can we fully polarize all of the nuclear spins in the system? So this has never happened. There's actually one result I'm aware of in the literature suggesting almost complete polarization of nuclear spins. This is not regularly achieved, except perhaps just this one time. No one really knows why. No one really fully understands all of the limiting factors in this process of dynamic nuclear polarization. And one idea that's been around actually for quite some time is the idea of a dark state. And so I'll tell you more about kind of an intuitive picture of this as the talk goes on, but this was realized more than 20 years ago that really under sort of general conditions, you would expect that as you polarize the nuclear spins with the electrons, the nuclear spin subsystem should move toward a state that is decoupled from the electron spins. And it should be decoupled in a way that shuts off the coupling that drives dynamic nuclear polarization. I'll give you more of an intuitive picture for this, I promise, as the talk goes on. This was first predicted more than 20 years ago in the case of these self-assembled quantum dots. And there's been a huge amount of theory work in the intervening time, continuing to explore this in self-assembled dots, but also gate-defined quantum dots. This dark state has also never been observed until actually just very recently. And this will be the focus of the talk. I should say that in the past few years, there's been some indirect evidence for these nuclear spin dark states, looking at sort of reconstructed spin statistics of self-assembled quantum dots, as well as coherence times in some very exotic and unusual semiconductors. So I'll tell you about some work that we've done where we believe we are realizing and can explore this nuclear spin dark state that's predicted to occur. And I'd like also to draw your attention to this paper from the UK group that appeared on the archive at about the same time. Okay, so with that out of the way, let me now tell you about the experimental platform that we use. These are gate-defined semiconductor quantum dots. If you look down here, this is a typical example of the device that we use. There's a layered semiconductor structure. So in dark green here is a thin silicon quantum well. In light green are silicon germanium layers. And what happens when we apply positive voltages to the metal gates here in yellow, blue, and purple is that we can attract or accumulate electrons in this quantum well. And when we adjust the potentials on these gates, we can create, in this case, a double well potential here that contains 2 electrons. So we would say that there are 2 electrons in this double quantum dot here. Okay, if you were to take a cut through the semiconductor or kind of zoom in on the picture that I just showed you, and if you could visualize the electronic wave functions, you would see something like this. So here again, in this upper picture, this yellow strip is the silicon quantum well. These are the 2 spacer layers. If we zoom in along this box, here's this silicon quantum well. Here are these big electronic wave functions, right? They started their lives as block wave functions, but they're confined through this double well confinement potential. So they're rather large. I feel like you can imagine this is a surface maybe of constant probability of the electronic wave function. All of these green dots here are silicon atoms in the semiconductor crystal. Okay, silicon is almost, but not quite, nuclear spin free. So about 5% of the silicon atoms are silicon-29 in natural abundance silicon. And so just a few of these dots here have black arrows to represent the spin 1/2 of these few silicon-29 atoms. All right, so each of these electronic wave functions actually overlaps quite a large number, about 10,000 or so nuclear spins. So now let me explain to you how DNP occurs in this system. So I'm going to tell you a little bit about how electrons in double quantum dots behave. And so the thinking starts like this. So let's suppose we have 2 electrons in a double quantum dot. If we symmetrically bias this double well potential, the ground state has 1 electron in each dot. We'll call this the 1-1 charge configuration. Okay, if we go over to the right, both electrons will occupy the right dot. We'll call this the 0-2 charge configuration. And if we go over to the left, we have the 2-0 charge configuration, which is the ground state. Here is kind of a cartoon energy level diagram showing how this works. Okay. If we decide to allow coherent tunneling of electrons through this potential barrier, the sharp crossings between these different charge states turn into avoided crossings. And most of the results I'll tell you about, all of them, don't have enough energy really to access the excited states. So let's agree to be happy with the lowest energy branch in the system. Okay, so we're talking about electrons. You remember that electrons are spin 1/2 particles. They're fermions, so we need to consider exchange statistics. We need to consider the Pauli exclusion principle in this scenario. So there are 2 electrons, each with spin 1/2. So there are 4 spin states that we need to think about. For my money, the best basis to think about for these 4 spin states consists of the singlet and the 3 triplets. We could pick up, 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 down, down, up, and down, down. Okay, but the singlet and triplet basis is a little bit nicer. So here they are. Here's the singlet, and then the 3 triplets. The singlet is antisymmetric under particle exchange. So what that means is that the orbital state of these 2 electrons needs to be symmetric under particle exchange, so that the overall state, which is the product of the orbital wave function and the spin state, is antisymmetric under particle exchange. One of them needs to be symmetric, the other needs to be antisymmetric, such that the product, the whole thing, is antisymmetric under particle exchange. So what that means is that the singlet, in particular, can easily have both electrons in the lowest orbital of the right dot here. If you like, you can imagine that we're filling the lowest orbital in a cartoon picture with 1 spin up and 1 spin down, just like you do in chemistry. It's also perfectly reasonable to write the 2-0 singlet state with both electrons over here in the ground state orbital. So this is not true of the 3 triplet states. The triplet spin state is symmetric. So that means that the orbital state of the 2 electrons, if they have the triplet spin configuration, needs to be antisymmetric under particle exchange. That's so that the total state retains the overall antisymmetry. So what this means is that we can't have both electrons in the ground state orbital of the right dot, say, if they're in the spin triplet state. If we want to put both electrons in the same dot, and if they have the spin triplet state, one of them needs to occupy an excited orbital. And so what this means is that for modest values of this tilt of the double weld potential here, this parameter epsilon, the three triplets stay blockaded, we say, in the 1-1 charge configuration. This is called the Pauli spin blockade. And this fact turns out to underlie almost everything that's interesting, which is quite a lot, about electrons in double quantum dots. Okay. So another way to look at this Pauli spin blockade is the energy difference between the singlet and the triplets here. This is a spin-dependent energy in the absence of magnetic fields. It's determined entirely by the Pauli exclusion principle together with details of the confinement potential. Okay, so if you look here at this star, you see that the T- state here, the down-down state, crosses the singlet state. These two states differ by the z component of the electronic spin angular momentum. The singlet has m equals 0. The T- has m equals -1. Okay, so you see that these two states, again, which differ in their angular momentum, have come into resonance. And they have come into resonance because of this Pauli spin blockade. The fact that the singlet state can bend down, but the triplets retain a constant energy with respect to this parameter epsilon is the reason that these two states come into resonance. Okay. Where this resonance happens depends on the magnetic field. So here you might imagine there's a small magnetic field. This splits apart the three triplets. Here's a larger magnetic field. It splits them more. You see where this crossing point is, depends on the value of the external magnetic field. Okay, that will become important a little bit later on. Okay, so this is one slide with equations here. I'll make sure to deliver the punchline here so you get this. So these two states, the singlet and the T- cross, they are coupled by the hyperfine interaction with the nuclear spins. So that is exactly what we want. That scenario is exactly what we want for dynamic nuclear polarization. Okay, so you can write down the hyperfine coupling Hamiltonian like this. Here's this I dot S. Here J indexes the nuclear spin, S indexes the electron spin here. Here capital R is the location of the nuclear spin, lowercase r is the location of the electronic spin. This delta function here is the thing that will eventually give us the modulus of the wave function squared, which you remember before. You can then compute the matrix element of this Hamiltonian between the singlet S and the T- states. What you find is that this matrix element is, in a sense, equal to the difference in the transverse magnetizations between the two dots. And by magnetization here, I mean the effective field that the nuclei exert on the electron. So here, for example, are the actual nuclear spin operators themselves. The cartoon way to think about this here is that this matrix element gives you, in effect, the difference in transverse magnetization. That's what the deltas here refer to. One dot compared to the other, and the Bx and By are the effective magnetic fields that the nuclei exert on the electrons. Okay, so dynamic nuclear polarization in the system is mediated by the difference in transverse nuclear polarization between the two dots. Here's kind of the cartoon picture for why this is the case. Let's suppose I have two electrons. Here's one and here's the other, and they're in an external magnetic field. Let's suppose that each of these electrons is coupled to its own nuclear spin ensemble like this. And let's suppose that each nuclear spin ensemble exerts a transverse magnetic field on the electron spin. So this transverse magnetic field here, if you like, is what we need to create transitions of the electronic spin states. If the nuclear magnetic fields, the hyperfine fields were all in the z direction, there would be no change in the spin state of the electrons. It's only when the nuclei can in one sense, exert a transverse field, or if you like, change the direction of the magnetic field that the electron feels, that we will experience a transition. It also won't do any good if the transverse magnetic fields from the nuclei are the same on both electrons, because then we would just flip both of the electrons with the same rate. And we would go from a singlet to a singlet, let's say, or from a T minus to a T plus. It's only when one electron feels a stronger transverse magnetic field that we preferentially flip one of the spins, if you like, going from singlet, an unpolarized state, to T minus, which is polarized. Okay. Let me pause and see if there are any questions. This is kind of a deep rabbit hole, so if you have questions, now is a good time to ask.
Just so that when two electrons are on one side, you mentioned that the higher orbitals are not allowed because they have higher energy. Their magnetic field is not that high.
Yes.
For the two electrons on each side, you can have singlet and triplet state.
Yes. Yes.
But you only consider both of them. But in your fourth state, you didn't put the orbital content, which doesn't matter for the green and blue, but matters for the red.
So
Right.
maybe we are
Is my question clear or no? I'm wrong.
not quite. Try it again one more time.
So when you're not when it's not so tilted,
Yes.
then you have one orbital.
Yes.
Indeed, you have to be in the antisymmetric.
Yes. Yes.
Spins.
Yes.
For the middle one, however, like I have two orbitals, left and right.
Yes.
So I can have triplet and singlet. Middle, the
Right here.
the red state.
The T0 or the S?
No, these three configurations that you have.
This one. Yes.
They can be triplet and singlet.
Yes. Yes. It can be triplet and singlet, but the orbital state still has a different character, which reflects the symmetry. And that, am I going along the direction you're thinking about here? Yes. And so that is the thing that gives rise to this this coupling here. So it's fundamentally the difference in symmetry between the orbital states of the singlet and triplet, which underlies this minus sign here. So here, this is making the Heitler-London approximation for the singlet and triplet orbital states that gives rise to this form of the coupling.
I'm just confused, like if the coupling matrix element is given by the difference between the magnetic field exerted by the
Yes.
nuclear spin, do you actually expect this interaction to fully polarize the nuclear spin? Like if in the ideal limit, like if it's only like if it only sees the difference between the two.
Yes.
Then like the statement of then polarizing it could be like what exactly?
You're eventually getting your way to the notion of this dark state here.
Okay.
But what I want to say is that if the nuclear spin configuration is such that there is a difference in the transverse component between the two dots, then this matrix element will exist. But you could imagine that in the case where they're fully polarized, there would be no difference in the transverse polarization. And that is true. But there's also interesting stuff that happens even on the way to that before. Yeah.
It's a question. So what is the direction of the process? Why you anticipate polarization but not depolarization?
There is a small external magnetic field that's yet larger than the magnetic field from the nuclei, which will determine the z direction. It's the fact that there is a triplet state with the preferred orientation here. It's that thing that sets the direction of the polarization. Okay, so how do we do this in practice? We use something called a Landau-Zener sweep. So if we imagine zooming into this crossing here between the singlet, here's the singlet curving down, and here's the T minus state here. It looks like a crossing on the previous diagrams I showed, but if you zoom in, This is actually an avoided crossing. Here, this delta ST is the size of that is the matrix element that I showed you on the previous slide. It depends, remember, on the difference between the transverse polarizations of the two dots. So then, given a particular matrix element here, we can change the horizontal axis. Here is this detuning parameter, the tilt of this potential well. We can change this detuning parameter through this avoided crossing, and depending on the speed that we ramp this detuning parameter, we can make an adiabatic transition from singlet to T minus. When we do this, the electronic state changes its angular momentum, and you can imagine that there's a corresponding change in the angular momentum of the nuclear spin system here. So then the idea to polarize the nuclear spins would be to do this many, many times. So after having done this once, we immediately go back over here, we initialize the electronic system as a singlet. We do this by exchanging electrons with the reservoirs. We change the angular momentum of the electronic system independently of the nuclei, and then we do another Landau-Zener sweep through this avoided crossing. We do this many, many times.
How do you get back to the left side without the adiabatic sweep?
If you like, we can do a diabatic sweep, go from here very quickly over here, say as a T minus, and then we exchange electrons with the reservoirs.
You're on the upper branch or the lower branch?
We typically initialize. We initialize always as a singlet through electronic exchange with the reservoirs.
Why do you end up in the upper, higher energy? When you do that one
Yep.
initialization.
Yep. So the initialization will actually happen over here. Will happen over here, and we'll exchange electrons with the reservoirs where this is the ground state by quite a bit. Sure. Yep. We're on the lower branch at that point. Yep. But maybe just to make the point here. So this avoided crossing is much smaller than this tunnel coupling. So diabatic with respect to this avoided crossing is still quite slow relative to this one. So even diabatic here doesn't excite us up to the other.
You think it's easy for just sort of zoom through the crossing and then you transition from the upper to the
Yes.
lower to the upper,
Yes.
and
Yes.
then you can probably expect that.
Yes. 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 Okay. So then this kind of a thing also has been known for many years in gate-defined quantum dots, this mechanism of dynamic nuclear polarization. Here are some experiments from gallium arsenide devices. Here's an experiment tracking the position of this crossing over lab time here. And you can see that it slowly drifts to the left here. This is an indication that the magnetic field the electron feels is changing as you polarize the nuclei. This is understood to be an indicator of dynamic nuclear polarization. Again, the question of is this process, because in these older devices, nowhere close to full polarization was ever achieved, remains an important one. All right, so we set out to explore this in silicon quantum dots. You could ask, maybe for the sharpshooters in the audience, why would you want to study dynamic nuclear polarization in silicon quantum dots? After all, again, if you're in this field, one of the main reasons to discard 3-5 materials in favor of silicon is that you can remove a lot of the nuclear spins from the system. But this is potentially an advantage if you want to study these nuclear spin dynamics, because there are many fewer of them in silicon than in gallium arsenide. There's still a lot, but there are many fewer of them, which makes the problem easier to study. The evolution of the nuclear spins is a bit slower, and they're more coherent than they are in gallium arsenide. All right. So now here's the data. So this is an experiment where we monitor the position of this ST minus crossing. So here's the detuning parameter epsilon here. This blue stripe is the location of this ST minus crossing. We're just doing an experiment where we prepare the system as a singlet. We wait near this ST minus avoided crossing, and then we measure. And then we do this for, this is probably about 30 seconds or so of actual lab time. All right, so you can notice a few things in this graph. First, this ST minus position drifts to the right as we do this process over and over again. So that's an indication that the magnetic field experienced by the electrons is changing as we do this experiment. Remember, where this crossing happens depends on the effective magnetic field. We're not changing anything about our superconducting magnet in this situation. The only thing that's changing is that we're repeatedly, we think, polarizing the nuclear spins. So this is an indication that nuclear polarization is occurring. We've checked that the shift is much, much faster than the drift of our superconducting magnet, for example, or things like this. The other interesting thing, though, about this, the thing that's perhaps more interesting, is this signal, the peak signal, actually gets dimmer as time goes on. All right, so as we do this more and more, the probability for the singlet to make a transition to the triplet decreases, even though we're not changing anything about how we run the experiment. And actually, this is certainly not seen in these experiments in gallium arsenide. So this would be kind of the equivalent panel in gallium arsenide. And here lab time goes down. If you look, it actually gets brighter as time goes on. Here we're seeing the opposite thing. So that's interesting. To focus in on this effect, we did a more precise experiment. So what we did was to initialize the system as a singlet, perform one Landau's inner sweep through this transition, and then measure the transition probability. That's the probability that we measure a transition to the triplet state. We're going to repeat this 64 times. And then we're going to wait a relatively long amount of time. This is to let the system partially relax. The nuclear spins partially relax to slow down the dynamics a little bit so that we can measure them. The important part here is that we're doing a sequence of 64 Landau's inner sweeps. We're measuring what happens after each Landau's inner sweep. What we see is that this transition probability, it starts at about 0.2, and then it rapidly shuts off after about 10 LZ sweeps here. Okay, so that's a more precise study of what I hand wavily showed you before. This transition probability becomes less. The transitions become less likely as time goes on here. Here, this is very dramatic. It shuts off very quickly. Okay. The other thing that we can do is in this configuration with this low transition probability, we can get a sense for how long the singlet would remain a singlet if we prepared it and just immediately change the detuning to that value. So here we're going to do an experiment where we prepare the system as a singlet. We'll do a Landau's inner sweep. We're going to do the same thing 64 times. And then what we'll do is we'll do a quick measurement essentially to go near this singlet triplet avoided crossing and wait for a variable amount of time. So when we do this, this is what we see. So here's the detuning parameter on the x-axis, this wait time here on the y-axis. You can see this very faint stripe here. So blue here is a singlet. Past yellow would be a triplet. If we omit this part here, here's what we see. So what you see here is that at this particular value of the detuning, if we prepare a singlet, and if we wait at this avoided crossing, there is a non-zero probability that we'll measure a triplet after some period of time. But that probability almost goes away when we are polarizing here. So up to as long as we could conveniently measure here, there was essentially no evolution away from the singlet when we're doing this pumping. So here, what this is telling us, the fact that this is dim here, this coupling is very small, and then let's say the rate of relaxation of the singlet is significantly longer under conditions of pumping than without. Yes.
These 64 pumping cycles, they take some time.
Yes.
So how this time can compare with the time with the lifetime of the Oberhauser field direction? So
That's an excellent question. Let me come back to that in just a little bit. Maybe that's even next year. So now to get at this question, which is how long does this configuration with this reduced coupling last? That's kind of where you're going. So to measure that, what we'll do is we'll we'll do 256 Landau-Zener sweeps to make sure we're in this configuration with the small coupling. Then we're going to wait a variable amount of time here. And then we're going to do one more Landau-Zener sweep after this variable wait. And what that will let us do, this final Landau-Zener sweep will let us characterize how long does it stay in this configuration with the minimal coupling. So here on the x-axis is this wait time, going from 0 to 10 milliseconds. Here is the Landau-Zener transition probability of this sort of probe LZ sweep here. So you see that after a few milliseconds, it recovers to the time, it recovers to the probability that it was before we did anything to it, okay? So what that time is, I'll come to in just a second. The pulses that we were doing here, maybe I'll just say this set of 64 pulses here is on the order of, let's say, a millisecond or something. So it's not the total recovery time, but it's also not infinitesimally short compared to that. Okay, so the transition probability recovers after waiting for a few milliseconds. Okay, so here's now what we understand is happening in this situation. So remember that this hyperfine coupling between S and T minus is the difference in the net transverse polarization of the nuclear angular momentum between the two dots. So to get a feeling for what's happening here, let's play my new favorite game here. Is this a zero gap or zero coupling configuration of the nuclear spins? Okay, so this is where I need some audience participation. So let's suppose we have two dots, a left dot and a right dot. And let's suppose these 4 green circles with their arrows are the nuclear spins associated with each dot. So you're looking down at the transverse plane for each of these 2 dots. Okay, so remember that the hyperfine coupling between S and T minus depends on the difference in the net transverse polarization between the 2 dots. So I ask you, is this a zero coupling configuration, a zero gap configuration of the nuclear spin? Seeing some nodding. Yes, definitely. Okay. How about this? Is this a zero gap, a zero coupling configuration between the, no, seeing some shaking heads. No, it's too easy. All right, you all have this. Okay, how about this one here? This is a little bit trickier. This is kind of like a random set of spins for each dots, but not quite. Okay, if you like, you can kind of focus on the left 2 in each dot. Are the transverse polarizations the same between the 2 dots? Maybe. I'm trying to make this harder on you. Maybe they look similar, but not quite. But one thing we can definitely do to make the transverse polarizations the same is we can just tip those that were different out of the plane. Okay. Now all we're left with are these parts here. But the difference in the transverse polarization between these 2 parts, that's just 0. So we're back to a zero coupling configuration. So we started from something that wasn't. Okay, we went to something that was by tipping them out of the plane. And then if I allow, maybe you missed it here, maybe this was too subtle. If you focus on the right 2 spins, if I allow them to move just a little bit, then we've spoiled this delicate alignment. And this is no longer a zero coupling configuration. All right, so this is essentially what we understand is going on in the system. If you understood what I just told you, you understood most of what's happening in the data here. So the way to imagine the formation of, now I'll call them dark states in the dynamic nuclear polarization, is that during a Landau-Zener sweep, the electrons exert a magnetic field that the nuclei feel. It's an effective field. It's called the night field. What that night field does is go from essentially up to down during this Landau-Zener sweep. When it's in the plane, it will tend to rotate any transverse angular momentum of the nuclei out of the plane and into the z direction. But the weird thing is that rotation only happens to the extent that there was a difference between the transverse polarizations in the first place. That's the thing that determines the size of the matrix element. So to the extent that there's a difference between these transverse polarizations, the nuclear polarizations will try to rotate out of the plane a little bit during this Landau-Zener sweep. That's the process of DNP. But you see that it also happens only to the extent that there's a difference to begin with. So the right way to think about what's happening here is that any difference in the transverse polarizations that exist in the first place effectively gets rotated out of the plane toward the z direction. That's the process of DNP, but at the same time, the difference that was there diminishes. And so then the process of polarization drives the system into this dark state with no coupling between the singlet and T minus states. Yes.
So when I was first looking at this data, I sort of thought, well, each time you traverse the intercrossing, you're going to flip one nucleus.
Yes.
Delta
Yes.
mass of
Yes.
one
Yes.
nuclear spin.
Yes. Yes.
But it sounds like maybe that's not the right picture.
That is not, even though that was the cartoon picture I showed you, the right thing to think about. They all tilt a little bit. They all change their orientations a little bit during this. Yes.
And so there's no, like, one thing I was considering is when you go through the anti-crossing, but perhaps you could actually see like a single nuclear spin flip as part of that. But it's more like you have to think of the ensemble of nuclear spins.
At the level of what I'm telling you, we think about it as the ensemble of nuclear spins. There is a very interesting line of research asking how precisely and how quickly can you measure the hyperfine field itself? And it is possible with these systems to measure a change in the hyperfine field that is close to that of a singular nuclear spin. And then maybe eventually where you are going with this is what quantum effects are visible in the system. I've been discussing this in terms of a classical picture mostly, and that's also a very interesting question. Okay.
Seem like the time scale, but it makes me then to relax in milliseconds. And, this microseconds you were sort of doing things. So
Yep.
you like make the dark state then.
That's a super great question. So that comes up at the very end. Maybe let me just, before I get your question, let me make one point though. So the final thing that matters here is that it's actually dephasing of the nuclei that spoils the dark state. It's actually not a nuclear T1 process. It's a nuclear T2 star process because there's this alignment in the transverse plane, which is sort of perfect in this dark state. But if it drifts a little bit, then the dark state becomes brighter. So that's starting down the road to answering the question you just posed.
So Paul, the next question. So you said every time you go for the sweep, you sort of align the nuclear spin, but isn't it only every time you go to the sweep and also flip? If you are staying in the singlet state, are you aligning them, or is that only happening when you take like a quanta of
certainly if the matrix element exists, and if we, yes, perform the Landau sweep and then measure the system to have undergone a transition, then it's at that point we imagine the angular momentum.
happens like 2 times. You have like a transition of the 0.2, and after certain times you sort of run out of sweeps in the other times.
I missed it. Try it again.
So I'm saying, if I started the singlet and I do the sweep and I end up to the triplet, obviously I've like shifted the nuclear spins.
Yes.
But then it only happens like 2 times on average.
Yes.
Sort of
Yes. Yes.
The rest of the time, are you shifting the nuclear spins? If I started singlet and then singlet, are you doing anything to the nuclear spins?
So what I want to say here is that in that case, we would imagine that the electronic state has been entangled with the nuclear spin state during the process of this Landau-Zener transition. In principle, I end up with a superposition state. And then formally, we would want to say, depending on the measurement outcome, angular momentum has been transferred. I'm not really saying anything I didn't already say. I think you can imagine at a classical level that yes, most of the time, nothing is happening, or most of the time at this classical level, the nuclear spins are all just changing the orientation a very small amount. Maybe we could talk a little bit more after if I didn't get it.
Sorry, just to refer, so maybe just following up. If I go to the single state and I just come back, I start in the single state,
Yes.
I ramp and I just come back, no
Yeah.
transitions,
Yeah.
then presumably didn't even get entangled. Right?
In that case, yes.
Then nothing happened.
Yes, yes.
Right, so it's sort of like there's very the like. Yeah, okay. I'm just saying. So the nuclear spins are essentially like 2 flips away from being polarized in some sense. It's
You're asking why did it go away after like 10? You're given the fact that it only died after 10.
10 times point.
Sure. So okay, I'll come to that in just a second. So the point of this slide is that dephasing is the thing that spoils the alignment and brightens the dark state and what I just showed you before. Here's a set of movies that I'm going to skip. So the dashed lines that were on the on the data plots were the results of a simulation of a semi-classical model where we treat the electronic state quantum mechanically. We compute the night field. The components of this are these deltas that the electronic state exerts on the nuclei. We keep track of what this night field does to each of the 10,000 or so nuclear spins in this system. And then we recompute the matrix elements between the electronic spin states. Okay, I'm going to skip this. So here's the data that you showed before. What we imagine here is that the nuclei start in a random thermal state. To the extent that there's a difference between the transverse polarizations, that gets transferred to longitudinal polarization. That's when the system then enters this dark state, and then the dephasing, the slight rotation of the nuclei in the transverse plane spoils this dark state and brightens it. There's no longer a vanishing difference between the transverse angular momentum between these two dots. Okay, so the simulation, which is in this dashed line here, assumes a nuclear spin T2 star time of about 4 milliseconds. So this is consistent with measurements of nuclear spin T2 star times in related devices. Okay, we're using a nuclear spin T1 time. That's the time for a nuclear spin to spontaneously flip from up to down, let's say, of about 20 seconds. This is consistent with our measurements. And we're keeping track of about 12,000 spins in this simulation. Okay, simulation agrees reasonably well with the data. In this case, the dashed lines again are simulations of what's going on here. One question you might have here is, in this case, without pumping, without polarization, why does this triplet probability not go to 0.5? In effect, we're just jumping to this avoided crossing and waiting for a very long time. Should the states just not completely mix? And should we not get 0.5? The reason there has to do with the fact that there are electrical fluctuations in the system. So if we could go exactly to this avoided crossing and stay there, we would expect an equal mixture. But instead, if we can't always hit this avoided crossing because of electrical fluctuations in the system will never completely mix, and there will be some preference for the singlet state, which is what we initially started with. Okay, so these simulations here include electrical fluctuations in the system. Okay, so then the final, going the wrong way here. One of the most interesting questions about all of this, though, it a little bit gets back to what we talked about earlier, which was it takes us only about 10 LZ sweeps with a relatively small transition probability to enter this so-called dark state. Now, that's a puzzle because for any random initial state of capital N nuclear spins, the net polarization on any direction is approximately the square root of n. So if we have 10,000 nuclear spins, we'd on average expect a random polarization along any direction of about 100. Okay. So what that means is that if I have two dots, their transverse polarizations will also be of order 100 spins each. And the difference I would also expect to be of order 100 spins. So what this means is that we would expect, in order to reach this so-called dark state, we would need to do about 100 LZ sweeps, or we would expect to need to flip about 100 nuclear spins to erase this difference in the transverse polarization. But we see that this happens in only about 10 sweeps. Why? The reason is that there is a substantial nuclear polarization that actually builds up during this process. So based on our simulations, we expect the nuclear spins are between 5 and 10 polarized, between 5 and 10% polarized during the course of this experiment. Here's the initial state here. So here they're polarized by 1% or so at most. Toward the end, they're between 5 and 10% polarized. If you think about, let's say, a random initial state like this, and if you imagine that the effect of these LZ sweeps is to rotate the nuclear magnetization by some angle. So if we go from this dashed line to the solid line, we're rotating by, I don't know, 30 degrees here. You see we start from here and end up here. If this initial state here, this dashed line, is more toward the z direction, you see if I rotate it by the same angle, so if I go from here to here, the reduction in the transverse part of this is much bigger than here. So here I maybe reduce the transverse part by maybe 50% or so. So I went from this much to about this much. But here I went from about this much all the way down to about here. So what we think is going on here is there's sort of a classical geometric effect here, that as the system becomes more polarized, this rotation of the nuclear spin polarization by these LZ sweeps more effectively produces this transverse polarization and hastens the appearance of the dark state. Okay, so I'll just wrap up. I've shown you the evidence, the experimental data, and how we understand it. There are lots of open questions. Can we reverse it? Can we brighten it? If we could brighten this dark state, does that open a path to full polarization of the system? There are interesting effects having to do with spin overcoupling in the system. The model that I've shown you treats the nuclear spin system as just a classical ensemble of spins. There are a lot of interesting quantum effects that are predicted to emerge. It should be useful, for example, as a quantum memory. So there's a lot we think that's exciting to explore. So thanks for your attention. I'm happy to take any more questions.
So normally I think of Landau-Zener sweeps as going through the avoided crossing, slowly, but then out to a pretty far, out the other side, and then measuring there.
Yep.
And you pointed to stopping sort of where you think the avoided crossing is, and then there's some charge noise, so that's not perfect. But sort of curious why you try to stop in the middle as opposed to just going all the way through.
The technical reason, let me say we could do that. The technical reason that we do it is that this way shows us perhaps a little bit more clearly where exactly that position is. But I think what you're proposing could be just as easily done. In this case, what we would want to do would be to halt the Landau-Zener sweep at various points, and then do that as a function of time. Let me also say, in this case, we were imagining that this is sort of a lifetime experiment for the quantum state. So this also shows us sort of the lifetime at specific points in this energy diagram, as you like, and we would not be able to measure it quite as directly with LZ sweeps.
So in this talk you mentioned about initializing the nuclear spin state into the dark state. So I'm wondering if it is possible to make any other nuclear spin state, or does this continuous transition always lead you to the dark state?
It is not easily possible to initialize other states for the reason that I mentioned at the top, which was that the Zeeman splitting is so small. We imagine that this is one of the best ways to initialize it into a particular state, although there are many dark states, actually. There's an infinite number of these dark states, an infinite number of configurations where the difference in transverse polarization vanishes.
I'm just kind of interested in if you said there are roughly 8,000 resistance in one, 4,000 in the other. And so just trying to think about how this fact depends on that difference. If you got to a very extreme situation,
Yeah.
presumably you couldn't get into the
Yeah.
dark state because it couldn't match their kind of polarizations and one that will hit 3 nuclear spins and the other one had 100.
Yes.
Right, but is that something possible to study or it's just too hard to do?
Yes. Yes. It's a good idea.
Just change it, find the potential to make the wave function smaller or something like that.
Yeah, I think it's a great idea. Absolutely.
I think we've run a little bit long, so let's thank John again.